So we just grew these crystals at McMaster University by the traveling solid floating zone method. And basically, well, I guess I should say, strontium copper borate's a quasi two-dimensional system. It's a quantum dimer. So what we found while doing USR, I guess well, I should say USR is very similar to NMR, and we just use the muon spin instead of the nuclear spin to detect magnetism. If you want to learn more about that, then come by and visit me at the poster. But anyways, we just saw in the USR that muon was perturbing our system and locally breaking these dimers. And so we saw similar things in the dope cases, but it was a little more complex. So I guess that's all I have to say for now. If you want to know more, then come to the poster.
Okay, thanks, Alan. Ailton, okay, great.
Do it.
Hello, my portion is orthogonal polynomial. There is a mistake there. Orthogonal polynomial Brownian motion ensemble. Correlation functions in the entire case. We study equilibrium Handel matrix theory. We use it, for example, to solve DMPK equation in quantum wires. Here we use these orthogonal polynomial ensembles. We solve the Fokker-Planck equation, characterizing these polynomials with delta initial function. We make a mapping from Fokker-Planck equation to a Hamiltonian of type Calogero-Saturn, and we calculate the correlation function of these systems in the unitary ensemble. Thank you.
Okay, Alexander Villegas. Is not there. Well, I'm still waiting for Alexander Villegas. Are you here, Alexander?
No, we're not.
Okay. Okay, so Alexander Lopez. There you go.
Hi. Well, I'm highly correlated with this conference and with this school because I'm working in quantum entanglement. We are trying to prepare to fermion entanglement from a Fermi C and study these scattering processes in which you create correlations among these particles, which in principle are non-interacting. We use a very simplified model of a two-level system as a scatter. We have found that the excitation of this two-level system increases the correlations among the particles which initially weren't correlated. If you want to get more information, you know where to find me.
Okay, great, cheers. Ali Francisco Garcia Torres. There you go, Ali.
Well, my name is Ali Garcia Flores. My poster presentation is a study of Raman scattering as a function of temperature in three specific materials. These materials are multiferroids. This material presents antiferromagnetic transition temperature around 40 Kelvin. The main point of this of the study is that we found characteristic temperatures below which anomalous frequency behavior occurs in these materials.
Yes, my work is the dependence of the hybridization in a DP Hubbard model. Well, in this work, we use the DP Hubbard model with the D and P bands and a local column interaction and a car-dependent hybridization. Using the two-pole approximation, we compare our results for normal and superconducting states with those in which the hybridization parameter is maintained constant.
Thank you. Carlos Alberto Vaz de Marie Jr. Did I get it right? Oh no. sorry.
Okay, hi, I'm Arvind from University of Chicago, and I'm studying a bunch of non-interacting electrons, so there is no interaction, but if you put in disorder to electrons, basically they can go from a metal to insulator, and we study such metal-insulator transitions in low dimensions which cannot be accessed by perturbation, so you have to use non-perturbative techniques. And one main feature of wave functions at such a critical point between a metal and an insulator is they are neither extended nor localized. They have a multifractal nature. We study this multifractality behavior near a boundary using both analytical and numerical techniques.
Now it's Carlos.
This work analyzes a fermionic Ising spin glass model with a transverse field. This problem is written in a grand canonic ensemble, with the spin operators are represented by a bilinear combination of fermionic fields. The transverse field is a spin-free mechanism that inserted quantum fluctuations. On the other hand, the effect of chemical potential is introduced charge fluctuation, what changes the number of occupation. The main purpose of this work is to study the competition between the paramagnetic and spin glass phases with both charge and quantum fluctuations.
Thank you. Now it's Carlos Monton.
My work is a superconducting response of superconducting ferromagnet niobium cobalt superlattices. The work starts trying to measure and to compute the gap, the superconducting gap under this condition in a multi-layer. But during that we found that at the mesoscopic scale there are a lot of interesting phenomena which can be used to technological applications. For instance, for thin cobalt layers, the superconducting layers are the couple, and for thick cobalt layer, the straight field and the applied field interact in a very interesting way and give rise to several phenomena. Thank you.
The work I present is based on the experimental findings in strontium gluconate 327. Strontium gluconate 327 is a bilayer compound that exhibits at very low temperatures, and in other free samples some anomalous phase, which is characterized by some large resistivity. So as you apply a magnetic field perpendicular to the bilayer planes, you will encounter a phase with large resistivity, which is also bounded to lower fields and larger fields by metamagnetic transitions. And more recently, it has been observed that there is also a large resistive anisotropy in this system present. And the possible suggestion for this is the formation of an electronic nematic phase out of an isotropic fermi-liquid phase. And this nematic isotropic phase transition can be studied with a simple phenomenological model. And we applied this model to a bilayer system and also find magnetic field, intermagnetic field, and the results are presented on the poster. Thanks.
Thank you.
The work presented in the poster is actually in collaboration with Claudio Chamon. I apologize for the missing reference in the abstract. Forgot it. Detail. It's concerned with the issue of quantum phase transitions that do not satisfy the Navier-Stokes criterion. In particular, we focused on a system exhibiting quantum topological order. We applied coupling that drags the system out of the topological ordered phase into a Landau-Mills type ordered phase. We show that this happens at a finite value of the coupling constant through a continuous phase transition. And despite this, we show exactly, with the exact calculation, we show that the topological order survives throughout the whole disordered phase and dies exactly at the transition, despite you start having finite correlations during this phase. That concludes it.
Thank you.
And I will.
Daniel Garcia.
Hi. Well, Eduardo has already introduced you to the dynamical mean field theory. What I will be showing in my poster are the TMRG results of solving the MFT equation. There you will see the doping result of the Hubbard model and also some results of the Hubbard model. That's all.
Okay, thank you.
Hi, my name is Daniel Reyes. The title of my work is Cursor from 2-dimension to 3-dimension anisotropic quantum lattice. This work is with Professor Mucio Continentino. Basically, we make a mean field approximation in a quantum necklace model. Our main result is to think that there is a critical line of nil when we turn on the anisotropic ring. Thank you, and I hope for this.
Oh, okay, fine.
So, I'm not the dot I just represent me. So my name is Letícia Mendonça Ferreira. So in my poster is about the pressure tempered phase diagram of lanthanum and tin-doped zero rhodium indium 5. So zero rhodium indium 5 is antiferromagnetic, have fermium, and it becomes superconducting under pressure. So we propose a combined study about the effects of pressure and doping on zero rhodium indium 5. And for that we have studied two kinds of doping. So we have studied lanthanum and tin-doped sample. And we have performed heat capacity and resistivity measurements under pressure, and we compare the obtained phase diagrams, temperature, pressure phase diagrams of the doped sample with those of the pure sample.
Eduardo Herri.
First, I would like to apologize for the wrong author list on the booklet. I forgot to send all the author names, so only my name appeared. And this will be corrected on the last version. My poster presents the pressure temperature phase diagram of the compound cerium 2, rhodium 1 - X, iridium X, indium 8. And this diagram was based on electrical resistivity measurements only. The diagram shows two zero resistance regions, possible superconducting regions, and one of them is induced by pressure and the other is suppressed by pressure. There is also one of the samples used to build the diagram seems to show reentrant superconductivity, and the results are presented in the poster. Thank you.
Okay, next victim.
Okay. My work is about the whole of the hybridization, the pre-hybridization in a VP Hubbard model. The model presents a narrow B band in a wide B band, a term of hybridization between this band, and a local co-interaction between the electrons. We investigate the whole of the hybridization, the band structure in the fab surface, the length of state, and in the superconducting properties of the model. Thank you.
Hi, so I'm Enrico Rossi, and I'm going to present the work that I did with Dirk at the University of Illinois at Chicago. And so, probably you know that in these DWAVE superconductors, people still argue about the nature of the collecting mode. So some people say it's a spin density wave, some say it's like a charge density wave, and some people recently also experimentally tried to convince us it's a phonon mode. And so what I'm trying to do is like let's say if you have an impurity and you pin this mode, and then you expect to have some clear signatures in the density of states due to the pinning of this mode. So you create a droplet, and then this droplet will show up. So if you want to know what fingerprints you have, come to my poster. And since I'm from Italy, we can also argue who has the best national soccer team. Thank you.
Okay, Eric Adriana.
Hi, I'm working on an extension of the MFT called StatDMFT. The main objective of this is to include special variations and in order to capture the Anderson localization. We are working on a square lattice, studying the disorder Hubbard model, and our preliminary results shows the screening of the disorder due to the interactions and also an enhancement of the conductivity. Thanks.
Okay, Eric now.
Ladies and gentlemen, boys and girls, children of all ages, the McMaster University Department of Physics and Astronomy is proud to present a poster about sodium nickel dioxide and lithium nickel dioxide. Two materials, two quantum antiferromagnets, two triangular lattices exhibiting geometrical frustration. One undergoes iontotal distortion, one does not. No one knows why. Lithium nickel dioxide, the material that does not undergo iontotal distortion, could exhibit a spin orbital liquid, or it could just have lattice defects and a strong sensitivity to disorder. To find out what we're doing to solve this mystery, come see my poster and prepare to be amazed.
Hi, so I don't know if I can top that, but so you can read my title up there. So I'll be talking about the cerium-rhodium-indium-5 system, which is a heavy fermion antiferromagnet, as Letitia described earlier. And it's the sort of system that Pierce is describing actually in his lectures. And we believe this is actually one of the prototypical heavy fermion quantum critical point type of systems. So I'd be happy to talk about sort of the general features that we see there and why we're excited about it. Or I can also talk to you about the cadmium doping and cerium cobalt indium-5, the very new results that we have, and the differences that system shows to the prototypical rhodium system under pressure. That's all.
Hello, good afternoon. My name is Germán Serrano. In this poster, I present a study of the correlated enhancement of the other critical field and critical current density in carbon nanotube doped magnesium diboride. Yeah? We made a sample with different content of carbon nanotube, and we observed two different effects. Part of the carbon substitute the boron site and enhancement the upper critical field, and remain as part of the carbon tube remain as tube and actual of vortex spinning. Yeah, and in this manner increase the critical current density. Thank you.
Hi, I'm Julian, and from my poster you will find out how you can grow two-dimensional superconductors with transition temperature really close to the quantum critical point. I'm measuring the superfluid density, and I'm looking for the effects of thermal phase fluctuation on superfluid density. The effects are there, but if you want to see them, please come around my poster. Thank you.
Okay. Coming? Oh, hand up here. Okay, Jose Rodriguez. Here.
Hi, so I will be talking to you about measurements we have performed at the microscopic scale in lithium yttrium holmium fluoride at very high dopings. This system have been shown some anomalous AC susceptibility measurements where in the highly doped regime where it was expected to be a spin glass, and instead
people have called this anomalous behavior as anti-glass. So we did neospin relaxation measurements in this system to get information on the magnetic ground state, and just drop by and I will tell you more about it.
Great, thank you.
I want to fill as professor for 1 minute. So, I just to make a poster, just to compare some cerium and ytterbium compound close to the quantum critical point, especially because if you imagine a cerium as when applied pressure, the volume reduces to the non-magnetic phase, and ytterbium you have an electron hole, okay, comparison close to the quantum critical point, but the phase diagram is completely different because in the magnetic phase, cerium compound usually exhibit the Donish diagram, while ytterbium shows nearly weaker dependence in the magnetic side. So I hope to see you in my poster.
I want to use the black one too. So in this work, my collaborators and I want to propose a way to probe the abelian and non-abelian quasi-particles in fractional quantum Hall states, which is 5/2, 12/5, and the Lambda states. And the geometry we propose is very special. Like it's a two-edge geometry, two quantum Hall edges. But what is so special is that after every tunneling event, if the quasi-particles satisfy fractional statistics, after every tunneling event, you change the tunneling probability. So it's very sensitive to statistics. So in this case, you can have a very strong experimental signature about to test the existence of those quasi-particles. And those quasi-particles are very important because you can build quantum computers with them. So if you want to know more about it, please come to my poster. Thanks.
I'm Laila Matos. If you come to see my poster today, I will tell you about using a scanning tunneling microscope to assemble atomically precise spin lattices and to use it to probe correlations if they arise in the system. So my system is basically cobalt atoms on a copper surface. This system exhibits the single impurity combo effect. Using the scanning tunneling microscope, I can probe the coma resonance and get from it the coma temperature. I can also move atoms around and build lattices out of them, and I see that the coma temperature changes as I do that. And so that could be a sign of correlated behavior in the system. So I can tell you more about it if we come to this again.
Hi. In my work, I synthesized the compound, the series, calcium 2-man I'll be a teacher in it. Calcium 2-man stack. Okay, please. It's better now? Yeah. X.
12 minutes.
Okay. Oxygen 6. And then I investigate the evolution of the series while changing X from 0 to 2. Interestingly, the ground state of the series changed from antiferromagnetic in the 0 and 2 values of X to ferromagnetic in the middle of the region, when you have approximately X equal 1. Thanks. Sorry about the English.
Hi, we will also use the blackboard shortly. I study disordered and correlated systems. So if I have no disorder, then I can observe a mode transition from a metal to an insulator as a function of U. If I have no U, no correlation, I have only disorder, then I can also see a metal insulated transition as a function of disorder. In my poster, I will show what happens as a function of U. I have finite U and finite W. In particular, I will explore some scaling properties that appear here when I have W larger than U. That's it.
Marietta Cameron.
Hi, my name is Marietta. I present a study of the quantum critical behavior of the antiferromagnetic conductive serial cobalto germanium silicon, a moderate heavy feather. We obtain donut phase diagram for this system using as a control parameter the hydrostatic pressure aimed at identify a possible quantum critical point. We performed electrical resistivity measurement at low temperature, 100 millikelvin, and pressure up to 12 kilobar.
Thank you. Mateus Lima.
Okay, my work is in the field of density functional theory, DFT. Advances in DFT depends on the development of the new exchange correlation functionals. And the implementation, the next task, the implementation of these functionals is no a easy task. So in my work, I will present a very simple way to make the implementation of the complex functionals in DFT. Well, thanks.
Hi, my name is Matthew Case. I work at the National Magnetic Field Lab in Florida. The general question we're interested in is what is the effect of disorder on quantum critical points in magnetic systems? So we study in particular a system of itinerant antiferromagnet where we know the transition at zero temperature between a cluster glass phase and a paramagnet. So what we find is that by looking at the rare regions which are devoid of any defects that come from the randomness, we find that fluctuations in the rare regions lead to a first order transition at zero temperature instead of a conventional quantum critical point. So we want to hear all about this. Come on over.
Hi. Okay, this poster will present the use of micromechanical oscillators to study magnetic properties of mesoscopic high disease samples. These oscillators are very sensitive magnetometers and their resonant frequency variation can be positive or negative depending on factors such as sample size, geometry, and anisotropy. These factors determine how the currents and magnetic moments are generated in the sample. In this case, the sample is a viscodisc with a diameter of 13 microns and a thickness of 2 microns. And we discuss our results based in the existence and contribution of inter and intralayer currents.
Pedro Bortuzzi.
Hi, I'm Pedro Bertuzzi. My work is a DMRG approach to the attractive Hubbard-Kondo model. And it's a model proposed by my advisor that incorporates two tendencies present in some superconductors. One is superconductivity, and the other is the magnetic ordering of localized electrons. What I do is study the ground state of this model through the DMRG method to find the properties, and I propose a phase diagram. Thank you.
Hello, I'm Rajdeep and I work with Professor Mohit Kanderia in Ohio State University. And there are two parts to this work. The first part is we have developed some sum rules for low-mode insulators. These are local sum rules for local density of states. And these are independent of any symmetry of the ground state or any such things. And this explains the striking particle-hole asymmetry in the tunneling spectra. Using these sum rules, we proposed a way to measure the local charge density variations, and the Cornell group of Seamus Davis has actually done that. In the second part, we looked at superconducting state, and we found that this asymmetry comes from incoherent spectral waves. We have also looked at violation of Latimer's sum rule in this systems, which has recently been measured in R-based experiments. Thank you.
One of the fundamental ingredients in frustrated magnetism is the ability to form spin singlets, which are the pair of a spin with its time reverse twin. So in order to do this, we need to have time reversal property be obeyed properly in a large n limit. So when we generalize SU2 to SUN, we find that half of the spins reverse properly and half of them don't reverse properly. So if we restrict to the subgroup of the spins that reverse properly, we find a new large n expansion. And when we use the Hamiltonian built exclusively from these symplectic spins, we find that we can treat a problem like the 2D Heisenberg lattice with the frustration and find the finite temperature Ising transition in our EV picture, which has never been seen before. So if you want to understand that more clearly, then you can come see my poster. Thank you.
Kuzminski.
Hi, so I do a mean-field study of the metamagnetic transition in the Fermi system. As we saw today, as you increase the magnetic field, for example, at zero temperature, you can drive a heavy fermion from an antiferromagnetic state into the heavy fermion state. But if you even crank up more that magnetic field, you can actually destroy the heavy fermion state. And there is also a change in the magnetization and the behavior of the magnetization. So there are two different scenarios that try to explain that. One is called the continuous evolution of the Fermi surface, and the other one is the localization of the F electrons. And I tried with the main field study to see what the main field has to say about that. That's it. Thanks.
Okay, so usually we study quantum critical points in magnetic metals, but in my post I look at a very different system where we have an insulating system with a charge-ordered phase, and you can, namely the ferroelectric, and you can tune the ferroelectric phase to absolute zero using pressure. And this is interesting because it forms a new type of quantum liquid to explore, which hasn't been studied in the past. And in my post I present a simple model to understand what happens in this region, and also show some high precision data in the strontium titanate system to see what happens. And it turns out that the ferroelectric may form an exemplary case of a quantum critical point, because there's no complicating factors of electron damping in insulators, but also in a narrow region close to the quantum critical point, there's still a possibility of seeing new behaviour, which you can see in the poster, including particularly if you have if you introduce electrons to the lattice.
So quantum corrections to the dual conductivity in low-dimensional weakly disordered systems are determined by the dephasing rate or dephasing time, which is the typical time scale in which charge carriers stay phase coherent. So in many experiments on the dephasing time, which the dephasing time is a function of temperature, by such conductivity measurements show that the phasing time as a function of temperature saturates for very low temperatures, which one cannot understand if one takes the electron-electron interaction as the main source for dephasing. So it became like common agreement knowledge that this saturation can be understood due to scattering of very low concentration of dynamical and especially magnetic impurities. However, the dephasing rate due to scattering from magnetic impurities was only known in the limit of very high and very low temperatures. So that was our motivation to improve the situation, and we had on one hand to face a problem of the Kondo effect.
And on the other hand, also to account for scattering from static impurities. And if you want to see how we did it, you should come to my course.
Okay, now we open the poster session, please.
So that everybody knows, there's a reservation for the real scenario in the name of Elisa, and the reservation is supposed to be kept until 8:30. So there's going to be a group of people that is going to go ahead of time, make sure that they hold on for the reservation. But let's try to finish looking at the posters and go to the real scenario before we lose our reservation. Okay?